Record. So this is the final Zoom for heavy civil construction, Thursday night, May 7th, which is actually VE Day, Victory in Europe for the Allied Forces in World War II. I'm going to put that on the final, which is next Wednesday, May 13th, from 6 p.m. to 10 p.m. You will get 2 hours to do the test. It will strictly be on soils. So everything we've learned on soils is fair game. Again, the final Wednesday, not Thursday. I apologize for trying to switch it, but it works better for everybody on Wednesday, May 13th, 6 to 10. And so what we're going to do now is we're going to finish up on soils. And the first thing we're going to do, can you see the YouTube? I think.
Yeah.
Okay. This is we're not going to watch the whole 8-minute YouTube. Hopefully, if you've watched it. If you haven't, you should watch this stuff before you do come back in the fall, because you're going to be running these tests. And this is a great screenshot because it really reinforces the fact that you're gathering at least 4, sometimes upwards of 6 samples at different moisture contents. And you can see the color of the soil as we start from the driest, just a little bit of water. Then they add another, they have a second sample, okay, whether it's 5 pounds, 6 pounds, 7 pounds, depends on the size of the aggregate. And that second sample has an increasing amount of water content. Then the third one, and then the fourth one. So again, it's a great shot that really reinforces that you're just not running one proctor. You're running 4 to 6, and then that takes us into the XL that we did. We started on Monday night, where we had a data sheet that half of the data sheet was for the dry unit weight determination, which was just hammering that soil in that proctor mold with the proctor hammer. And then if you remember, after they were done weighing the mold with the compacted soil in it, they took the soil out of the mold and they grabbed some of the soil. They grabbed 2 samples for each trial. This is trial 1, trial 2, trial 3, and so on. They grabbed 2 so as to give them an average. We're just going to grab 1 in this example. So the first one, they had 12.98 minus 9.45. So just the weight of the soil was 3.53 pounds. And that volume of the mold is 1/30th of a cubic foot, which means it takes 30 of those to make 1 cubic foot. So you take 3.53 times 30. If you go to the this little part upper left where it shows the formula. So again, this is yours to keep, this XL. We'll be using this when we actually run these tests. Now that gives you the wet unit weight in pounds per cubic foot. We have not determined the moisture. Okay, so they took a sample of the moisture, a sample of the soil, the wet soil. Even this one has a small amount of soil. So they're all either damp or wet soil samples. Going back to this, we had weighed the cat food can. We had weighed the can, which is the tear, right? The tear plus the wet soil was 172.11 grams. These are all in grams right here. These numbers are arbitrary. That just depends on the size of the cat food can. So we weighed it wet. We threw it in the oven. We shake and bake it. We weigh it dry. The difference between the two, you can see O22, so this is O22 minus O23 is equal to the weight of the water. Now, the weight of the dry soil is not this because we got to take the weight of the cat food can out of it, or what they call the tare. So 139.76 minus the weight of the can. 023 minus 025. These are the cells. Okay. And then moisture content, which you will have a moisture content calculation on the test. So take a look at this Excel. Okay. And now in this formula, you do not see it as being multiplied by 100 because right up here, I've called it a percentage, and Excel will burp that into a percentage automatically. So then you take the data, you take 80.3 and about 32%. And you go to your data, and let's do a smiley face. Is there one where there's a scowl for a curmudgeon? I don't see it. Okay, so we're going to go with this. So this was 32 and 80.3. So there's about 32, 80.3. Whoops, that's a little too much smiling. So there's your data point. Then for the next one, that was 82.4 and 33.6. 82.4, 33.6 is right about there. And there's your second data point. Okay. Last few data points. Data 3, that's 13.19. That's 13.20. 13.18. 13.11. That's the beauty of Excel. Okay. Now, right here, we go through and do a bunch of, that's 192.45 and 152.11. And that kicks in our moisture content. Okay. So, I don't know if you have all these numbers. So it'll take me 2 seconds. So this is 171 point, I should have done this earlier, 07, 184. Whoops, hit the wrong damn button. 167. There is no pattern of the weight of the cat food can. There's no pattern on these weights. The only pattern that you're looking for are the moisture contents in relation to the dry unit weight. 6, 42.1, 128.44. Okay, so if you go to, there's a handout that I showed you that gives you the formula for the dry unit weight, which is the wet unit weight, which is this, 105.9, divided by 1 plus the moisture content. Well, what's 1 plus 31.9? It's 1.319 because that 31.9 in decimal form is 0.319. So you want to take a look at how to run those calcs. And there was a, if we have time at the end, I'll go over that. But that's, it's a kind of a nasty little calc. So the next, I'll just do one more plot, and then eventually we're going to come back to this Proctor curve in another handout. So this was like 35 and close to 83. So there's 35, right there. And then guess what? What is the dry unit weight doing? It comes up to a certain point, it reaches a maximum, and then it starts to go down with increasing moisture contents. And what you, Yes. Well, the water is starting to displace the soil particles. Water is lighter than the soil particles. It's always a constant volume. So that's why your dry unit weight goes down. And that's, you always want to plot the dry unit weight. So at 38 and 81.5, there's 38, and I'm just going to wing this, in 81.5. And then the last one was 43 and 76. Okay. So there's your Proctor curve. And then the shapes that you're going to do is you just connect the dots. All right. And there's, whoops, I always do that. So let's do my favorite button, which is the undo. And right there, and we'll just play around with that. So there's your Proctor curve. Okay, I think this is the first time in 30 years I put smiley faces on a Proctor curve. So the bottom line is, what do you do with that? What do you do with that curve? Well, the Proctor test is a lab test. And so now in the specifications, there are specifications, and you have this one. This is soils handout number 2. It's in the soils folder at the top of Vanco Hall. And so here, this is the ET spec. Okay. And I'm not going to worry about this 3% drier or 2% wetter. We'll talk about that in the fall. But this is what we're looking at. Okay. Compact each layer of fill and backfill for the following area classifications to the percentage of the maximum density specified below. Well, here it's 95% of what you achieved for your maximum dry density. That's 95%. Could be 98%, could be 90%. It depends on the soil. It depends on the, is it topsoil? You know, are you doing landscaping? They're even requiring you a certain compaction for that, so you don't make it too light and you sink out of your foot sinks right into the dirt. So it's a percentage. The field compaction is a percentage of whatever you get for the maximum dry density. And that's the other part of this Proctor, which is at 6 minutes and 40 seconds. Okay, right here. So this could be 95, it could be 98, it could be 90, it could be 85, which is very rare. This right here is the maximum dry unit weight, the top of the bell-shaped curve. And wherever the top of that, the peak of that curve is, you drop straight down. And that moisture right there is what we call the optimum moisture content. Optimum meaning best. Optimum meaning best. So we're going to go through a step-by-step on how to use this Proctor curve for field data. And again, this is dry. This is the dry side of optimum and the wet side of optimum, because water content is increasing as you go from left to right. So that brings us to the Denver case study. Okay, you have this in Vanco Hall. Hopefully you've taken a look at it. If you haven't, you might want to for the test, because I'm using a lot of the theory here. So right under this week, Proctor Nuke compaction. Okay, and this lab packet soils is where the formula is for calculating dry unit weight. Handout number 4, using the Proctor. explaining the Proctor is in this. And then I threw in the Excel that I've been using down below. Okay. And then this site eval case study, DIA, stands for Denver International Airport, or Do It Again, had a slight cost overrun, a couple $2 billion. So let's go to the DIA case study. Now, a lot of this, since we're just running out of time, you know, remember we talked a little bit about this. This is the concrete graveyard after they had some issues with concrete. Here's an overview of the from the FAA tower. This is where they parked the birds. So all of this soil had to be brought up or either cut or filled to a subgrade elevation so that they could then place the concrete aprons, tarmacs, sometimes they call it, the runways themselves. Okay, here's another shot. You can see the runway off in the distance under construction. And here is a good pic. This is the original grade at this area. You can see where the power line was. And so what they did is it's called a mass balance. And so they cut the high spots and they move it over to the low spots. Okay, so this is the grade after cut. We're moving soil, the earth, to another area on the site that needs to be filled. So cut and fill. Okay, this excavator was retrofitted for installation of drainage pipe, and just some really cool. So there's our term mass balance. You can read that. This is the machine that literally sliced the soil about anywhere from 8 to 12, maybe, yeah, 18 to 24 inches into the soil. There's really no cobbles and boulders, if you will, out there. It's all, it's basically all clay, very small gravels, not big gravels, if you will. But this thing is really cool. So it's got a D10 powertrain to push it, a D10 dozer pulling it. And like I said, this thing pivots. So that part cuts into the soil goes up this conveyor, goes into another conveyor at 90 degrees, and then burps out the side into these. And these are called 777s. They may have changed the number since then. This is called a belly dump. And so that's what they use to transport the soil from where they cut it, where they slice it, over to where they have to fill in. Okay. And then they got grade stakes for fill. We're going to play around with that a little bit in surveying. Okay, so they're bringing up this subgrade. They're bringing it up to subgrade. Okay. And then that's just a picture of Royal Gorge, which is really cool, south of Denver. You've seen this before. There's my thumb or my index finger. There's the, this is the lime treated soil. Cement treated base, 17 inches of Portland cement concrete. Paver in action. This is why this handout's probably the best thing for you to use to study for the test. You know, why do we classify soil? What classification systems do we use? We just didn't get to New York State specs. We're going to actually play around with those in the lab in the fall. Okay, and then AASHTO is the highway, and then the hybrid is this project. It's a little bit of everything. So here's the Denver specs for soil classification. They allow non-expansive clays or siltstones between 25 and 80% passing the number 200 sieve. Between 80 and 200. I'm sorry, between 25 and 80% passing the 200 sieve. So if it's more than 50% passing the 200 sieve, it's a fine-grained soil. And it kicks in the left side of that chart that we generated for and I put it So here's the answer key. Okay, and here's the answer key for the, put this down here for the time being. Here's the answer key for classifying that soil. Both those soils were coarse grained because they had percentages less than 50% passing the 200 sieve. But if you had the Denver clay and you had anything greater than 50, right, then it would kick out, it would eliminate this part of the chart and this part would govern. And then you got to look at something called the liquid limit. So I'll probably throw a question on here. I'll probably throw one here and one here. Okay. So that's a little background on that. They talk about sulfates. You know, it has to have a maximum, only allowed a maximum sulfate content because sulfate is a naturally occurring compound in soil and it does attack concrete. And you can get a sulfate resistant type Portland cement. Now the way they work it is a select material means that you can use it. So you go through and you do, for these, you would do the hydrometer test, the plasticity, the liquid limit, because it is a fine-grained soil typically. If it doesn't meet any of the requirements, then it's called a non-select. Sometimes in certain projects, you'll see satisfactory and unsatisfactory, okay? So look through all these notes that I put on these specs, okay? And then here's some, this is all my writing. And then years ago, somebody did mention the best soil to build an airport on would be clean gravel. But they didn't have that there. All they had was clay. It'd be way too cost prohibitive to bring that much gravel to the site. So that's where they do the soil cement or soil stabilization, where they're mixing that lime slurry. That's a little theory right there. So here's the lime slurry for Denver. So it's mixed here, goes into this dump truck. There's a manifold on the back, and this, it looks like Christmas time in July. And then that's that big old rototiller that rototills that lime in and takes the plasticity out of the soil. And here's the sheep's foot roller that is used for cohesive soil. And cohesive soil is your clays and some silts. Cohesion-less, I don't know if I had a picture of it. This is for granular soils, you're going to use a smooth drum vibratory roller. The sheep's foot has these lugs, and here was a great shot where this soil had been compacted. This soil definitely was just starting the compaction process. And so through repeated passes, okay, repeated passes by this machine, the sheep's foot roller, you're going to compact that soil, okay, say to 95% of whatever the dry density was from this Proctor test. And there's the Proctor mold. So you've seen that. They also extruded what I call the soil hockey puck out of there because they had a certain spec for the strength of the lime treated soil. And they actually put that in a compression machine and they broke it. So the kicker is, how often do you test soil? And that's always in the specification. Now, in that spec handout number 2, right, you have ET, you have the federal, the USC federal, and there's DIA. Okay, so that's where I took that from. So here's the frequency of testing. Moisture density relations, that's the lab test. That's tied in with laboratory classification. You classify it to see if it meets the requirements for that specific type of project. Okay, so they say 5 tests at the beginning of the subgrade treatment and thereafter, but not less than 1 test per 20,000 square yards. Well, why are they talking about square yards? They're actually talking about area, a footprint, if you will, of the concourse, the tarmac, the apron where the birds, the airplanes park, and the runways. So basically say every 20,000 square yards, okay? Every 20,000 square yards, not square feet. So I'm going to multiply that by times 9. So that's about every 400 feet by 400 feet, you're gonna do a Proctor test. In place soil density and moisture. This is a field test. This is my writing. Okay, 1 test for every 1,500 square yards. So 1,500 times 9, and you will see some units on the test. You got to know how to convert from, say, square yards to square feet and vice versa. And so you got to know your units. Times 9 equals, and that's about every 115 by 115, okay? pH, that makes sense, lime content. That's the lime that they used for soil stabilization. There's your compressive strength, okay? And it had to be at least 250 PSI in 5 days at 100 degrees. And maybe if I can get some clay, we'll actually do some soil cement. We'll mix it. We'll break the son of a, almost swore. We'll break it in 5 days, see if it comes up to 250 PSI. It's very similar to the compression cylinders that you fabricated for statics and strengths. Okay. This was soil only. In other words, if they were not doing soil cement. Now, here's the key point. That's why I put, Jesus, there's a lot of asterisks there. The soil that you test for compaction must be representative of the soil sample that you used for classification. In other words, the soil that you tested in the lab better be the same type of soil that you're testing in the field when you compare the Proctor curve. So that's key, page 12, that is key. So there's some recap. Anytime when I say that, recap it. So the Proctor curves are used as a standard for site compaction. Long-term soil settling is called consolidation. That's a whole nother type of study, as is the word surcharge. We'll talk a little bit about that next semester. Okay. So here we go. Back to the Denver spec for compaction. Lime soil mixture. Okay. The field density of the compacted mixture, lime and soil in the field, shall be at least 98% of the maximum density of the laboratory specimens prepared by the contractor. That's the Proctor. And right here, this 98%, they're talking about dry density, and sometimes they call it the degree of compaction. Sometimes they call it relative compaction. And because it's 98%, they'll just say 98% of the Proctor. If it's 95, they'll say 95% of the Proctor. So that's some of the terminology that you use. I've emailed a couple of you who are interested in soils, and a couple of you are interested in surveying. But if you get to work for say an excavator, or even better, a material testing company, man, read up on this. This will help you for your job. The moisture content, this is a typical spec for clay where they want it, it always has to be on the wet side of optimum. I'm not going to test you on that. I'm going to test you on a little chart that I've made for you. This is a performance spec. It's identical to what we called the execution part of the ET spec. Remember? Or installation part. Part 1 was general information. Part 2 was products. Part 3 of the ET spec was installation. It's like a performance spec. This is how you have to perform it, and so on. So I just showed you that, for example. Well, what do you use to test in the field? You got to get moisture and density in the field. And it's called a nuclear density meter, or the nuke test. Now they're actually making non-nuclear. It's fascinating. The technology is unbelievable. There's a, damn it, where is it? It's right here. This is the whole template. So you put this template right here where the nuke is before you set the nuke in. Okay? You put that template, say, over here. You put this, oh my God, it's almost like a footing, oh, help me out, guys and gals, a footing spike or whatever. And you take this thing, actually this actually has the spike in it, and you pound a hole in the ground. And then the nuke sits on that, and this is a plunger that starts out at the top, and when you plunge it down, there's a steel probe that goes into that hole. And little photon torpedoes, that's technical from Star Trek, literally will tell you very quickly what the moisture and density is for the soil in the field. Okay? This is the sand cone. You might want to remember that for the test. The Romans used it when they built the aqueducts at Segovia and the roads that supported Segovia. We don't have a nuke because we don't want the nuclear issues. A lot of paperwork for that, and they're expensive. So we use the Roman sand cones. That's a joke. And I don't have time to go into that, but you will actually run that test in the fall. They also do something for testing stability. I'll show you what's known as shaky silt in the fall. Also show you the taste test for soil. Grosses people out, but you can do it. Just make sure it's inorganic soil. So this is a proof roller. There's tons of sand in this steel box. And you literally, there's somebody on the other side just looking at that to see if the compacted soil moves or pumps under the load. That's a proof rolling. So here's the step-by-step. This is what you got to study for the test this coming Wednesday. Again, Wednesday, May 13th. You run the proctor. That's the lab test. You graph the proctor. You highlight on the graph maximum density and optimum moisture content. Now for clay, the moistures are very high. For granular soils, like gravels and sands, they're much, much lower. Okay. The DIA, the specs, okay? I don't know why I put that, why I put the 2, but that paragraph said that the percent proctor, or relative compaction, was 98% of the maximum dry density. What's the word of mean in math? It means multiplication. So you go back to page 13 of this handout. So 0.98, 98% of the top of the, I knew I forgot to take that damn phone off. And I better get my cell phone. Let me just do that. Let's see here. 98% of the top of the bell curve, which is your maximum dry density, is the minimum density that you have to reach in the field. Okay? So, let's see, I'm just doing here. Okay. So, That 82.7 was the maximum. 98% of that is 81 pounds per cubic foot. PCF, pounds per cubic foot. So we need to have at least the nuclear density meter, or the Roman sand cone, needs to register at least 81 pounds per cubic foot minimum for us to meet compaction in the field. If it was 95%, then the standard is not as high. Okay? And then all of these steps go into this little chart for you. So these are the 1, 2, 3, 4, 5, 6. These are the 6 data points from the, actually I forgot one here. These are the data points for this soil sample. So I used it for Denver, even though it was from Texas. I said, close enough for government work. And so we're going to go back, and I'm going to give you a proctor curve on the test, and you got to do these steps. So the first few steps, you're actually running the proctor, and you get these data points in blue. Okay. Your maximum dry density was at 82.7. Your optimum moisture content was 35.7. So again, the end of 15, the beginning of 16. I'll tell you what, you go work for somebody and you get a good command of this theory, their heads are going to turn. Soils are very misunderstood. So everything we talked about here, right? 98% of. 98% of that number is 81, right? 81 pounds per cubic foot. So what you'll do is, step 6 says to locate a line across the graph for that minimum field density. Well, if you go to 98% of the maximum 82.7, which is 81, draw a line across the graph. How many points do you intersect the proctor curve? 2. You intersect it here, and you intersect it here. From the 2 points of intersection, project lines vertically down to the x-axis. It establishes a range of acceptable moisture contents in the field. A range of acceptable moisture contents in the field. In other words, and it's not exact science, but it's damn close. Between this point and this point, if you run that sheep's foot roller enough passes, enough times up and down on the soil that's being compacted, you should be able to get 81 pounds per cubic foot, which is 98% of the maximum dry density that you got in the field. Now, one thing we didn't talk about is when you moved that soil from the high points to the low points that needed to be filled, you have to compact that soil in anywhere from 8, typically 8, sometimes 12-inch lifts, L-I-F-T-S, basically a pancake. If you just move the dirt 4 feet vertical at a time and try to compact it, you'll never get the entire depth compacted to spec. You got to do it in thin lifts, L-I-F-T-S. Does that make sense or not? So, like I said, it's not back in 1977, so I won't smoke my Marlboro like my old teacher did. Okay. So here, if our soil, if our field test is between 32.5 and 38.5, we know with enough compactive effort of the machinery that we can get this minimum field density. So let's go through some of the tests. These are actual tests that I made up. That's an oxymoron. Sorry about that. DIA, Denver International Airport, Clay. Nuke results. We love nuclear power. See if everybody's awake. You guys awake? Whew, everybody's sleeping. Holy shit, it's the third course in a row. I don't blame you. So, shouldn't have said that. Hey, it's my last Zoom. So, do we pass or do we fail? So let's look at some test results. They're out in the field. They're using the nuclear density meter. And the nuclear meter says that I just went and popped a hole in the subgrade, used the nuke, the little photon torpedoes from Star Trek told me that the moisture content, it literally can tell the moisture content of the soil was 35%, and the density was 81.5 pounds per cubic foot. Well, 35 is in that range, and 81.5 is higher than 81. And this goes back to where the hell did I put it? Yeah, this goes back to the YouTube where they did that same horizontal line at 95%. They use 95, we use 98, right? 95% of whatever that maximum number, that maximum density or unit weight number was. Drew that line across, go right down, drop 2 vertical lines where it intersects the Proctor curve, and there's your acceptable range of water content. Okay, so we're just reinforcing what they said in that video. Now let's go to another test. Don't forget that in the spec it said that we had to run a in-place density test, which is the nuke, say every 1,500 square yards. And let's say that we went to another part of the runway, and the nuke told us that our moisture was 36.5%, and our density was 76.5. Well, the moisture, 36.5, is still in that range. So we're good with the moisture. But we're low on the density. That's the Greek symbol for density. I had to be 81 pounds per cubic foot, which meant that I don't have to mess around with the moisture. I just got to hit it with more passes with the sheep's foot roller and then retest it. And these folks, and there were a lot of women that worked out in the Denver airport. Actually, the chief of construction was a woman, just letting you know. So it was a great opportunity, as construction is, for women. So you do more passes with a sheep's foot roller. And again, the technicians and the contractors are really good at knowing about how many passes it takes to get compaction. That's also part of the, I think I might have X'd out of it. That was from the technical booklet that I had you look up on the internet. So that gets into the science, if you will, of the energy of, say, a sheep's foot roller or a smooth drum roller. Don't forget, the soil that you are analyzing with the field data versus the Proctor, they've got to be the same type of soil. And that, wait till you see some of the Denver Proctor data sheets that I'm going to show you in August. It's really hard to do. It's an art. So let's do another test. And we're getting into another 1,500 square yard footprint of the runway. Damn it, now that moisture is 30%. Well, 32.5 to 38.5 was my range. The density was 78. That makes sense that it's low. This is called the dry side of the optimum range. Okay, this is the optimum range right here. We're on the dry side. We're below 32.5. We're only 30. You literally got to rip it up. And what they used to do is they would rip it up with the teeth on ripping teeth on a bulldozer. You would add water. Do I have? And that's I have on a video. Oh, I did not get that converted. And I'm not allowed in Smith Hall to get the damn thing. So I'll do that. I'll do that for the fall for you. So you literally add water. It's a big water tank, and they use like a fire hose. And they add water. They mix the water into the clay with a. It's like a disc. It's like a farm disc. Okay, that's a big ass farm disc. Oops, sorry about that. BAFD. So farm disc. And then you check the moisture content with the nuke to see if you need to add more water, because the nuke, you can use the nuke just to check moisture content before you run all these passes. No sense in running a bunch of passes if you have not added enough soil or enough water to bring that up into the moisture optimum range. Okay. So again, you rip it up, you add water, you mix it with a farm disc, you check the moisture content with the nuke. If you're in that range, then you can recompact with a sheep's foot and you retest. You're going to have some test results questions almost identical to these. You have to know how to manipulate the Proctor curve. So then we did another test, another 1,500 square yard footprint of the runway. Now we're at 41% moisture. And our density is 76. Okay, well, 38.5 was the upper limit of the optimum range. We were at 41, so now we're on the wet side of the optimum range. What was I going to say? I forgot here. So when you're on the wet side of the optimum range, this is a problem. It's hard to do. You got to rip it up. You can either add drier soil, let air dry, tear out the wet soil, bring in some drier stuff. This one is a hard one to remedy. Okay? It's a hard one to fix. Adding water, if you're on the dry side of the optimum range, is much easier. Okay? You have to then recompact, retest, and you got to check it again. Not only do you check the moisture content, but you also check the density, the field density. Okay. What the testing labs did out there is they brought out mobile testing labs. They brought out a little trailer. They had all their equipment right in there. Because every once in a while you get this type. You got another test here. Now all of a sudden it's 25% moisture content. It makes sense that fails because that's less than 32.5. It's not in the range, the optimum range. But this part doesn't make sense. The density is 91.5 pounds per cubic foot. This brings me to an important point. These field tests do not fall on the Proctor curve. The Proctor curve is with that little rammer. Okay, that's only done in the lab. All you're looking for is, are the field tests acceptable dealing with the minimum density and the moisture optimum range? So these are not going to hit the curve. They may, but it's a fluke. This is used with the rammer. All of this compaction is done with the sheep's foot roller for this Denver project. We don't go running around with a bunch of those little Proctor rammers compacting the soil. That was a joke. So this means that the results from this soil test means that it's a different soil. We have to look at another Proctor curve. This data cannot exist with the Proctor curve we are using. So we pick a different Proctor from what they call the family of curves. And I'll show you that in August. And you look at the soil description and the classification. And you do what's known as a 1 point. Okay? You'll really impress somebody if you know what a 1 point is. If you can't figure out what Proctor curve from, say, and there were like 20 or 30 curves that they had to work with, because soil, when you test it, or just soil in general, varies quite a bit. As my boss out in Denver said, we're asking soil to be consistent, and it is anything but. As one contractor said, he used to have nightmares, and the two subjects of his nightmares were density and moisture content. So you can run a Proctor test in the field because they had a mobile lab. Right at the nuke test, grab some of that soil out of the subgrade and hammer it into a Proctor mold. The data point from there, the data point from a 1 point, which is a Proctor test in the field, will fit on one of the curves from your family of curves. This is an important fact. It's a hard one to describe because you're thinking, hey, you told us that the Proctor test was only a lab test. It is always a lab test, but sometimes it is used in the field when you're getting into different types of soil. Okay. Now, real quick, this, it's fair game and you should know how to do it. One more thought. That lime-treated soil, also known as soil stabilization, soil cement, or cement-treated soil, CTS, we put that the testing company put that hockey puck after it cured for 5 days. The lime literally stiffens the clay, and it should handle 250 PSI. Okay. Now, in the field, it did fail. Okay. In one part of the project where I worked, the lime-treated soil compression cylinders or compression samples failed. So what they had to do is, before they ripped out all this work that they had done, they decided to perform an in-place field bearing test. This is more statics and strengths, but the theory is the same. So they prepared a surface to kind of shaved the clay. This is Ottawa sand that we use for the Roman sand cone. You see that? You know what that is right there? That's a hand plane that you use for wood. They shaved that clay so it is a super flat site. And that's pretty picky, but they want to get a good flat surface for this piece of flat steel. And you see how it's built up? There's a whole bunch of them. Here you can see it even closer. So they lay these plates down and they're going to jack against it. But what do they use to jack against? A stinking dump truck, an end dump with a shitload of sand in it. Okay. Sam was a retired guy that came out of retirement and worked. He was one cool dude. He would be about 150 now. Well, just kidding. Really great guy. I learned a lot from him. So you have to pick a big enough counterweight so that the lime-treated soil settles first while jacking. These dial indicators can show movement as little as 1/1000th of an inch. Okay. And what happened was, and I don't have the pictures, I think I just have videos, and I'll get those converted. the actual strength of the lime-treated soil in the field confirmed the bad test results of the lime-treated soil hockey pucks from the Proctor mold. And $1 million later, I think it was $1 million. Let's just say it was $1 million. It sounds good. It's 25 years ago. They had to go through and rip all that up, and they had to put down a blanket of Portland cement and mix that in with that big rototiller, watered it, compacted it, and that's how they got their strength. In other words, you need a minimum strength of that soil to be able to support the runway. So this is a great handout. Where is that runway? Oh, there's the hockey puck again. So there it is. So this lime-treated soil has to be strong enough to withstand these two slabs and, of course, the weight of the airplanes taking off and landing. Let me just see, those are statics. We talked about soil handout number 2 with the specs. So I'm going to throw some questions at you about using specifications that may even be out of the Denver one. Okay, and that's about it. Let me go through my list. I'm not going to give you any homework. Your homework is you got to study for the final, or you don't have to study for the final. That's up to you. So we're not going to do that. We talked about specs. We talked about nukes. We graphed a few points. And really, I think your best bet is if you read this, as one of you said, you go through the Zoom and you read along with this handout. And it was fun actually making this handout as kind of a step-by-step primer for soils. It's very basic. It's geared more towards the technician in the field and the contractor, if you will, rather than engineering. But it does use some engineering concepts. So I know I threw a lot of, it's 7:35. We did go over a little bit. I threw a lot of information at you. Again, we'll do the final exam Wednesday, May 13th from 6 to 10 p.m. just on soils. So if we go back to Vanco Hall, right, we started soils. My God, how the weeks fly by. This is where we started getting into soils, all the YouTubes, all of the, not a lot of reading, fair amount of reading. And then we got into the sieve, the classification, the laboratory compaction, which is the Proctor, and then the field compaction. So, any questions? Hopefully you're still there. What I will do is we'll sign off here pretty soon. I'm not going to, like I said, no homework. And just keep looking over the, I'd say keep looking over the homework, and there'll be concept questions, there'll be mathematical questions, and so on. The one thing I could do, I don't like going on camera, but I suppose I could do it. Let me show you a quick, and this would help you because you might see it. So share the screen or share the, so I went out and bought a, I went out and bought a little roll of whiteboard material. So let's do a quick example for you. This will help you for the test. The footprint of the runway subgrade, where you had to do an in-place nuclear density test, they called it 1,500 square yards. okay? 1,500 square yards. How many square feet is that? Well, I'm glad you asked. Okay, so this is the dimensional analysis. I think I covered this. I know I did in statics, so if you're taking statics, you're in good shape. If I want to convert from square yards to square feet, then since yards, and you can say that it's over 1, even though you don't show it. If yards is in the numerator, where does it have to be in the conversion factor?
The denominator.
I think you're a bunch of Rip Van Winkles. I think I put everybody into a deep.
It needs to be in the denominator.
Right. So you got the yards. 1 yard is how many feet? 3.
3.
But because this is squared, we need to do what? Square the beast. And this is like a Dr. Seuss thing. You got to square everything within that bracket. This is when I write down CF, that is a conversion factor. So because this is squared, 3 squared, feet squared, 1 squared, yard squared, green eggs and ham, Sam I am. See, it's Dr. Seuss. Sorry about the shadow. Don't like it. Let me see if I can try something different with the lighting. Is that better? No? Okay. And then you got 1,500 square yards times 9, and you're left with square feet because, whoops, yard squared divided by yard squared is, it's 1. It cancels. Okay? Now, if you started out, let's say you started out, and you can do that because this is America. Let's say that you had, what would that number be? Right, that'd be 1,500 times 9. So it'd be 13,500 square feet. If I took the square root of that, shift square root, then it's about every 116 foot footprint, right? About every 116 foot footprint of surface area that you got to run a test on. And that's called testing frequency. Now let's just, for shits and giggles, whoops, shouldn't have said that. So let's just say that, I don't know, let's pick 2,000 square feet. And I want to convert that to square yards. I just made this number up. This is actually from the specification. Go back to your conversion factor. Right? Always put this over 1. Don't forget the math that I do is voodoo. Okay? I'm so old that I learned this and I don't remember, but they're all shortcuts. Because feet squared is in the numerator, it's got to be right here. 3 feet, 1 yard. If it were just feet, I'd be done. But it's feet squared. So now what do I got to do? Square the beast. 1 squared, yard squared, 3 squared, feet squared. Feet squared cancels. Like that. Now I've got 2,000 times 1 squared divided by 9. And now I have my area in terms of square yards. So I go 2,000, hit the clear button, 2,000 divided by 9 equals. Okay? So I'm going to throw a question like that on the test. You know, probably use something out of the Denver spec. and have you convert from one type of unit to another. And if you master this, you'll be in great shape for statics and strengths a year from now. If you don't master it, that's where the cheese starts to bind, okay? I don't know if I can say that. Well, I did. It's America, okay? So that's a little helpful hint on units. So let's go back to share the screen. Let's go back to here so I can get the hell off here. And that's about it, folks. I will now stop recording the Zoom for Heavy Civil for Thursday, May 7th. And the next time well, actually you won't see me because you'll be doing the final on Wednesday, May 13th. Wednesday, May 13th, not Thursday, from 6 to 10 p.m.